in a very long time. We believe that the early universe was a simple place. After the Big Bang, everything began slowly, bit by bit. Then, when the James Webb Telescope started pointing at a seemingly empty patch of sky and discovered the most distant galaxy ever observed, what made astronomers pause wasn't its distance. The problem lay in the fact that when the data was analyzed more carefully, people realized it wasn't alone at all, around it, and at similar distances. There were many other galaxies also emerging from the darkness. If these galaxies truly existed just a few 100 million years after the Big Bang, then the universe had to form structure much faster than what we ever thought. And if that's true, then the most distant galaxy is no longer a singular record, but the first sign showing that our picture of the early universe has a bigger problem behind it. When a galaxy is said to be tens of billions of light years away from us, that expression conceals an important truth in the universe. Distance is not a fixed quantity, and light does not travel through unchanging space. Light from distant galaxies doesn't just cross space, but it travels within a structure that is changing over time. That change is the expansion of space. In the modern cosmological model, galaxies don't simply fly away from each other like fragments of an explosion. Instead, the space between them is stretching. This has a direct consequence when space expands. Every wavelength of light traveling through it is also stretched along with it. This phenomenon is called cosmological redshift. Redshift is not a minor optical effect. It is a measurement of time. The degree to which light is stretched tells us how much the universe has expanded since that photon was emitted. A higher redshift means that light left its source at an earlier moment in the universe's history. The important thing is, redshift is not because the galaxy is running faster than light, but because the space between the source and the observer is continuously being stretched. Therefore, light doesn't lose energy due to collisions or obstacles, but because its very measure wavelength is being changed by the dynamic structure of the universe. The consequence of this mechanism is that light from the early universe becomes increasingly difficult to observe. Ultraviolet and visible light, originally emitted by young stars, when passing through billions of years of expansion, will be shifted completely into the infrared region. When redshift exceeds a certain threshold, that light nearly vanishes from the observational capability of optical telescopes. This is exactly the fundamental limit that has constrained astronomy for many decades. Hubble can see very deep, but it was optimized for visible light. When redshift approaches around 10, corresponding to just a few 100 million years after the Big Bang, most light from young galaxies has been pulled outside the range that Hubble can effectively capture. Not because these galaxies are rare, but because their signals are shifted into a domain that the instrument cannot keep up with. This creates a dangerous observational gap. When an epoch of the universe cannot be seen directly, it must be inferred. Cosmologists build models about how galaxies form, how stars are born, and how matter assembles. Then test whether those models can reproduce the universe today. If the results match, the model is considered reasonable. But this reasonableness depends on a key assumption that nothing unexpected happens during the epochs we cannot observe. If the early universe had mechanisms that were more efficient, faster, or statistically different from predictions, then the models could still reproduce the current universe, but with an incorrect formation history. In other words, the model could be right at the final result, but wrong about the path leading to it. A common misconception is that the age of the universe directly limits the distance we can observe. But due to the continuous expansion of space, light may have traveled for 8 billion years, while the current distance between us and where that light was emitted is much larger. This is why the diameter of the observable universe is many times larger than 8 billion light years. This also means when we look at galaxies with very high redshift, we are looking at an extremely young universe. But those galaxies today are not close in any intuitive sense. Space has stretched the relationship between time and distance to the point where ordinary intuition no longer applies. In this context, all conclusions about the early universe depend closely on how far we can track stretched light. If a telescope cannot capture most light shifted into the infrared, then it only sees the tip of a population that could be much larger. This explains why, for a long time, early galaxies seemed rare and small, not because they were actually that way, but because we only saw the brightest, most prominent individuals, objects that don't represent the entire population. But before James Webb changed this, there was a more important question that needed to be answered. What type of stars lit up the first galaxies in astronomy? The first stars of the universe have a specific name, population 3, or abbreviated as POP3. The name sounds backwards. Generation 3 is actually the first generation, but that's just a historical accident in classification. What matters is not the number, but their nature. POP2R are stars born in a completely pristine universe. No carbon, no oxygen, no element heavier than helium, only hydrogen and helium from the Big Bang, and an extremely small amount of lithium. In that environment, the physics of star formation changed completely. Today, when a gas cloud wants to collapse to form a star, it needs to cool down. The fastest way to cool is through molecules like CO, carbon monoxide, or dust-containing silicon. These things act like heat sinks, absorbing thermal energy, then radiating it away as infrared light. Thanks to this, gas cools quickly, fragments into many small clumps, and creates many stars with diverse masses. But in the early universe, none of that existed. The only available cooling mechanism was the hydrogen molecule H2, and it was much less efficient. The result is that gas cools slowly, doesn't fragment deeply enough, and when it finally collapses, it doesn't create hundreds of small stars like today. Instead, it creates a small number of extremely large stars. Theoretical models predict that POP3 had masses from 100 to 300 times the mass of the Sun. Some estimates even go up to 500 times. Such stars don't exist in the modern universe, because the metal-rich environment doesn't allow them to form. Because they're extremely heavy. POP3 are also extremely hot. Surface temperature can reach up to 100, 000 Kelvin, compared to about 0 K for the Sun. This means they emit most of their light in the far ultraviolet region, exactly the type of radiation needed to ionize surrounding hydrogen and illuminate the dark universe. But their lifespan is extremely short. A star 200 times the Sun's mass might only live a few million years, a blink of an eye, by cosmic measures, before exhausting its fuel and dying in an extremely powerful supernova explosion, or even collapsing directly into a black hole without exploding. When they die, they leave behind the most important legacy metals. In the cores of these stars, nuclear fusion creates carbon, oxygen, neon, silicon, iron, and dozens of other elements. When the star explodes, these elements are ejected into space, mixing into the interstellar gas. And from there, the next generation of stars, population 2. Then population I, like the Sun, can form in an environment that has been enriched. This is why POP3 are important, not just because they are the first stars, but because they are the prerequisite for everything that follows. The problem is, we have never actually seen a POP3 star. Before James Webb, no telescope was sensitive enough to detect light from a single star at redshift above 10. even if it was millions of times brighter than the Sun. The distance was too far, and the light was redshifted too strongly. James Webb changes this equation, but not in a direct way. Instead of searching for a single star, JWST searches for indirect signs of them in the light spectra of early galaxies. Specifically, astronomers look for spectral features that cannot be explained by ordinary stars alone. One of those signs is the He2 emission line helium ionized twice. To create this requires photons with very high energy, the kind that only extremely hot stars can emit. If a galaxy shows strong He2 without signs of an active black hole, that could be evidence of POP3 presence. So far, some objects have shown suggestive signals. In the JADES program, a small galaxy at redshift Z is approximately equal to 8. 5 has an extremely blue ultraviolet spectrum and weak He2 signatures. Some groups suggest this could be a galaxy undergoing its final POP3 star formation episode before transitioning to normal star formation mode. But definitive confirmation remains difficult, because POP3 don't exist for long. Within just a few million years, the surrounding environment has been enriched by metals from the first supernovae, and from then on, the next generation of stars begins to form. This means the time window to observe pure POP2e is very narrow, possibly only from Z15 to Z20. However, what's more interesting is even though we haven't seen POP3 directly, JWST data is indirectly confirming that they must have existed. The evidence comes from detecting metals in high redshift galaxies. In some galaxies that JWST observed at Z8 to 10, spectra show emission lines of oxygen, carbon, and even nitrogen. The presence of these elements means at least one previous generation of stars had lived, died, and ejected metals into space. If we're seeing metals at Z9, and if these elements were created by earlier generation stars, then those stars must have existed at Z12, Shiwu, or even higher. And those stars, forming in an environment without metals, are almost certainly POP3. This creates enormous time pressure. If POP3 had to form live, day, and enrich the environment before the galaxies that JWST is observing appeared, then this entire process had to occur within the first few tens to few hundred million years of the universe. This is one of the main reasons why cosmologists feel pressured by JWST data, not because there's something wrong with the physics, but because the pace of everything had to be much faster than what models had assumed. James Webb changes this at a fundamental level. By observing primarily in the near and mid-infrared regions, James Webb was designed to capture exactly the type of light that the early universe emitted, but previous telescopes couldn't retain. This not only expands the observational range, but also restores the connection between light, time, and source physics. When James Webb detects a galaxy at very high redshift, the data doesn't just tell us that galaxy exists. Its light spectrum allows determining the degree of expansion the light has undergone, thereby placing that galaxy at a specific moment in the universe's history. This is the difference between seeing and locating in time. Once this positioning becomes reliable, old assumptions begin to be tested directly. Galaxies appear at times when models predict structure is still primitive. They don't just appear individually, but with density large enough to become a statistically significant population. Here, the problem no longer lies in observational technique or how to interpret data. It transforms into a more fundamental question: if light has shown they exist at very early times, then physical processes must have operated in ways more efficient than what we had assumed. Looking back at the past, therefore, is no longer looking at a simpler version of the universe. It is confronting an epoch where physical conditions were different enough that the familiar rhythms of structure formation may no longer apply. And when those conditions begin to be exposed through direct data, the big question is no longer whether the early universe was complex, but how long we've underestimated that complexity. In astronomy, the more shocking a discovery, the stricter the verification requirements. And the first question is always, are we really seeing galaxies at that time? Or are we just being fooled by the instrument's limitations? James Webb was designed to face this question directly. Unlike previous telescopes, JWST doesn't rely on a single measurement. It combines multiple independent layers of information. The first layer is light sensitivity, with a primary mirror 6 femmeters in diameter. Webb's light-gathering area is about 6 times larger than Hubble's. This allows it to detect sources tens of times fainter, especially in the near-infrared region from 0 sex to fem micrometers. But high sensitivity, by itself, isn't enough to confirm distance. The key point lies in spectroscopic capability. James Webb carries instruments like NIRSpec and NIRCam, allowing not just imaging, but also splitting each galaxy's light into separate wavelengths. When this light is analyzed, astronomers look for familiar features, such as the Lyman break, a sharp drop in the light spectrum at wavelength 121 sex nanometers, due to neutral hydrogen absorbing ultraviolet photons. In the early universe, this feature is redshifted deep into the infrared region. The exact position of the Lyman break in the spectrum allows determining the galaxy's redshift with high reliability. This is not guessing shape or color, but a physical signature tied to atomic structure. When JWST observes galaxies with redshift greater than 10, even up to 15 or higher, the position of the Lyman break doesn't appear randomly. It repeats consistently across many different objects, in many different sky regions. This eliminates the possibility that these discoveries are just noise or confusion with closer dust-obscured galaxies. Furthermore, James Webb doesn't operate alone in confirming observational depth. Many of its deepest viewing fields, such as galaxy clusters in the Glimpsey or Cosmos Webb programs, were chosen because they create strong gravitational lensing effects. Clusters like ABEL-S 1063, with mass equivalent to hundreds of trillions of times the Sun's mass, bend surrounding space and magnify light from background galaxies by tens, even hundreds of times. This effect doesn't just make distant galaxies brighter. It also creates characteristic shapes, arcs, Einstein rings, and multiple images. These shapes allow astronomers to build mass models of the foreground galaxy cluster and test whether the position and distortion of the images are consistent with a source at high redshift. In other words, the distance of distant galaxies is not only confirmed by light spectra, but also independently verified by the geometry of curved space. Another important factor is exposure time. Some of JWST's deep fields accumulate over 100 hours of observation on the same sky region. Under those conditions, random noise decreases with the square root of time, while real signal increases linearly. This helps clearly distinguish between physical light sources and random detector fluctuations. The result is, many early galaxies don't just appear in a single image, but reappear stably across different filters, at different wavelengths, with intensity consistent with the same redshift. This consistency is the signature of a real discovery, not a technical error. When astronomers synthesize data from multiple observing programs, a noteworthy trend begins to emerge. The number of galaxies detected at redshift greater than 10 is significantly higher than predictions from models based on Hubble-era data. In some surveys, the density of bright galaxies at the time, just 300 to 500 million years after the Big Bang, is higher than predicted by nearly an order of magnitude. This cannot be explained simply by better telescope sees more. Models had accounted for that effect. The problem lies in even when adjusted for higher sensitivity. The number and brightness of these galaxies still exceed expectations. More importantly, these galaxies don't just exist on statistical paper. Many of them have measurable physical sizes. After correcting for gravitational lensing, up to several hundred light years. With star formation rates inferred from ultraviolet brightness, they are not gas clumps just beginning to form, but actively operating systems. At this point, the suspicion that maybe we're seeing wrong becomes increasingly difficult to maintain. Data doesn't just come from one instrument, one method, or one viewing field. It comes from the intersection of infrared optics, spectroscopy, gravitational lensing, and number statistics. When multiple independent methods all point to one conclusion, science must shift focus. The question is no longer whether these galaxies exist. The question becomes if they exist this early. Then, which assumptions about structure formation need to be reconsidered? Because at this point, James Webb is no longer simply a telescope discovering new records. It has become a tool forcing cosmological models to confront data, where previously they only relied on inference. For many decades, astronomy operated based on a very resilient intuition. The farther back we look, the simpler the universe becomes. Not because scientists were naive, but because all observational evidence supported that. Nearby galaxies are large, with clear spiral, bar, and disk structures. Distant galaxies are small, distorted, faint, and chaotic. Order seemed to emerge slowly over time. That order was encoded into how we build cosmological models. In the lambda CDM model, large structures cannot appear early. Dark matter creates initially very small halos, then gradually merges. Gas falls into these halos, cools, forms stars. Every step has delay. There are no shortcuts. Therefore, when James Webb was designed, it wasn't expected to overturn this picture. The initial goal was much more modest: push the observational boundary a little further. See galaxies a bit smaller, fainter, earlier than Hubble. No one seriously predicted that Webb would see many large galaxies at very early times. What happened was different. One of the first programs showing this was JWST Advanced Deep Extragalactic Survey JADES. JADES didn't target a special object, but chose sky regions already very thoroughly observed by Hubble, with the assumption that we had nearly squeezed dry the information from there. Webb only needed a few dozen hours to prove that assumption wrong. In JADES Image, the number of red sources objects whose light is strongly stretched into the infrared increased sharply. This was not a noise effect or image processing artifact. They appeared consistently across many different NIRCam filters, with energy spectra matching galaxies at very high redshift. More importantly, some of these sources weren't just existing, but significantly brighter than expected. Before Webb, models predicted that at redshift above 10, when the universe was less than 500 million years old, galaxies, if any, should be very small and very faint. The simple reason: not enough time for gas to cool, form stars en masse, and accumulate mass. But data from JDS shows many galaxies have ultraviolet brightness equivalent to dwarf galaxies in the modern universe. This is not vague inference. Brightness is inferred directly from photon intensity collected in specific wavelength bands. After correcting for distance and redshift, to ensure these weren't just fake red dots, JWST used spectroscopy to measure redshift directly. And this is where everything becomes serious. One of the most prominent sources is MOMZ14, confirmed to have redshift Z equals 14. This number doesn't come from color comparison or spectrum modeling, but from directly identifying shifted emission lines in the spectrum. This places this galaxy at the time when the universe was only about 280 million years old. No gray area. No possibly. This is a galaxy that truly existed at an extremely early time. And MOMZ14 is not alone. In the same data set, JADAS and related programs confirmed many galaxies at redshift from 10 to 13, with brightness higher than most pre-JWST models predicted. What's noteworthy is not the existence of individual cases, but their numbers in science. Numbers are what kills hypotheses fastest. If there's only one anomalous galaxy, we can invoke gravitational lensing, or a rare event. But when a population appears, those explanations quickly run out. To test whether this was just a special region, JWST deployed a completely different campaign, Cosmos Webb. Cosmos Webb doesn't go extremely deep into a small area. It spreads wide. During the period from 2023 to 2024, JWST performed 152 observations, accumulating 255 hours of exposure over a sky area of about 54 square degrees, a very large area by JWST standards. The result is the Cosmos 2025 catalog, with over 700,000 sources detected and classified. This number itself is already revolutionary. But what's more important is this catalog allows astronomers to measure galaxy density by brightness and by cosmic time, instead of just listing records. When doing this, a worrying trend for models emerges. At redshift from 8 to 10, the number of bright galaxies was already higher than predicted. But at redshift above 10, where models say bright galaxies nearly vanish, JWST still sees them with significant density. A prominent analysis in this series, often referred to as mirage or miracle, focuses on sources at redshift 14, 15. Based on survey area and number of confirmed sources, the authors estimate that the number density of bright galaxies at this epoch could be more than 100 times higher than pre-JWST predictions. This is a very strong statement, and it's not based on a beautiful image, but on statistics. At this point, the question is no longer is Webb wrong. The question is what in our chain of assumptions caused predictions to deviate so far. To answer, we need to return to how models are built. In Lambda CDM, the number of bright galaxies in very early times is limited by three main factors: the number of dark matter halos large enough, the efficiency of converting gas into stars, and the degree of feedback disrupting that process. Webb doesn't directly measure dark matter halos, but it measures the final result, light from stars. If this light is more than predicted, then at least one of the three factors above is being underestimated. One possibility is that star formation efficiency in the early universe was much higher. In a low metallicity environment, gas cools through a different mechanism. Fragmentation can lead to more massive stars, emitting stronger ultraviolet light. This doesn't violate physics. It's just different from conditions in the modern universe that models are typically calibrated to. Another possibility is that large dark matter halos appeared earlier. This doesn't require changing the nature of dark matter, but may require adjusting how initial density fluctuations develop into nonlinear structure. Importantly, no simple explanation can resolve all contradictions at once. And that's exactly what makes the situation interesting. James Webb isn't saying the model is wrong. It's saying the model is missing detail, exactly where we previously couldn't observe. Here, a key point needs emphasis. JWST doesn't just see farther. It changes the observational mode. With high infrared sensitivity and precise spectroscopic capability, Webb transforms speculations about the early universe into measurements. Looking back at all the data, one conclusion becomes clear. The universe, in the first 500 million years, was not a slow, clumsy place. It was a dynamic environment, where gas collapsed quickly. Stars formed early, and light appeared more densely than we ever imagined. This is not a minor detail. It directly affects every subsequent question. How fast did reionization occur? How did primordial black holes form? And what role did small galaxies play in shaping the large universe? In every story about the early universe, there is an epoch seen as the boundary between invisible universe and observable universe, the epoch of reionization. This is not a vague concept or symbolic. It is a specific physical process, measurable, with direct consequences on how light travels through space. About 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. From that moment, the universe entered what's called the cosmic dark ages, an epoch lasting hundreds of millions of years, where there were no stellar light sources, and neutral hydrogen absorbed most ultraviolet radiation. In that environment, light couldn't travel far. The universe was optically nearly blind. Reionization occurred when the first high-energy radiation sources, stars, galaxies, and possibly black holes, emitted enough ultraviolet photons to ionize neutral hydrogen, separating electrons from protons. When hydrogen is ionized, the environment becomes more transparent, allowing light to travel across cosmic distances. The question is, who did this? And how fast? Before James Webb, the answer was largely based on indirect inference. Measurements from the cosmic microwave background radiation, CMB, indicate reionization completed around Z is approximately equal to 6, when the universe was 1 billion years old. But the start time was vague. Models typically assumed reionization started slowly, accelerating gradually as the number of galaxies grew large enough. This assumption was based on a key condition. The number of galaxies emitting enough ionizing photons in the very early universe was limited, not because physics forbids it, but because Hubble couldn't observe deep enough and wide enough to verify. James Webb changes exactly that. Instead of searching for a few extremely bright hero galaxies, JWST allows astronomers to count the number of galaxies by brightness in very early epochs. This is a difference in principle, because reionization is not determined by a few rare bright sources, but by the total number of photons emitted by the entire galaxy population, especially small and faint galaxies. The Cosmos Webb program plays a central role in this transition, with 255 hours of exposure spread over 54 square degrees. Cosmos Webb doesn't just provide beautiful images. It creates a statistical sample large enough to construct the luminosity function of galaxies at high redshift. The luminosity function answers a very specific question. How many galaxies are there at each brightness level at a given cosmic time before Webb? This function at Z is greater than 8 was nearly extrapolation. Now, it is data. When groups analyzed Cosmos Webb and JADE's data, combining deep and wide catalogs, a clear trend emerged. At redshift from 8 to 10, the number of bright galaxies is not only higher than predicted, but the slope of the luminosity function at the faint end slope is also steeper. This is very important. A steeper slope means when going down to fainter galaxies. numbers increase very rapidly. These galaxies faint, small, but abundant are the main candidates for producing enough ionizing photons to reionize the universe before Webb. Many models were forced to assume that faint galaxies at Z is greater than 8 were either very rare or inefficient at emitting ionizing photons, due to being obscured by dust or due to internal feedback. JWST data is shaking both those assumptions. Observations from NIRCam show many early galaxies have very blue ultraviolet spectra. In astronomy, blue is not aesthetic color, but a sign of young stars, massive, and very little dust. Dust absorbs ultraviolet photon. Little dust means higher ionizing photon escape fraction. Escape fraction is a key parameter. It indicates what percentage of ionizing photons produced by stars actually escape from the galaxy and enter the intergalactic medium. In modern galaxies, this number is typically low, just a few percent. But in small, dust-poor early galaxies with sparse gas structure, escape fraction can be much higher. James Webb doesn't measure escape fraction directly, but it measures indirect signs, ultraviolet spectral slope, emission line intensity, and galaxy morphological structure. When these signs are combined, they paint a consistent picture. Many early galaxies are more efficient photon factories than predicted. This is reinforced by discoveries at the extreme end of time. Galaxies confirmed at redshift above 10, like MOME Z, 14 at Z equals 14. 44 show that photon sources existed when the universe was only 280 million years old. This is the epoch that previously many models still considered too early to contribute significantly to reionization. No one is saying MOME Z 14 alone reionized the universe. What's important is it proves that light sources capable of emitting ionizing photons existed very early, earlier than the time frame many models defaulted to. When combining this with galaxy density measured from Cosmos Webb, a logical consequence emerges. Reionization may have started earlier and proceeded faster than pre-JWST scenarios. But reionization is not just a problem of having enough photons or not. It's also a problem about the spatial structure of the ionization process. In the early phase, reionization didn't occur uniformly. Ionization bubbles formed around light sources, grew larger, then overlapped. The size and growth rate of these bubbles directly depend on galaxy density and brightness. JWST data, especially when combined with observations from ALMA and Lyman alpha surveys, allows astronomers to begin inferring the size of ionization bubbles at very early times. Some results suggest these bubbles may have been larger and appeared earlier than predicted. This is consistent with a scenario having many faint but efficient galaxies, rather than just a few extremely bright sources. Here, an important point needs clarification. James Webb doesn't directly see ionized hydrogen. It doesn't observe free electrons flying through space. What Webb does is measure the source of photons, and from that infer ionization capability. This is how science works when directly observing a process is impossible. We measure components, build a photon budget, and test whether it's sufficient to explain the observed state of the universe. And when this budget is updated with JWST data, many old models begin to show deficits. One more factor increasing pressure on models is cumulative star formation rate. When integrating the luminosity function over time, we can estimate the total amount of stars formed up to a certain time. JWST data shows that a significant fraction of stars in the universe may have formed very early, in the first few 100 million years. This is consistent with independent conclusions from detecting metals in early galaxies. Metals elements heavier than helium can only be created in stars. JWST's detection of emission lines of oxygen, neon, and nitrogen at redshift 7.9 shows that at least one previous generation of stars had existed and died. The presence of metals this early reinforces the argument that stellar activity occurred more vigorously and earlier than predicted. When placing all these puzzle pieces together, the reionization picture begins to change. Instead of a slow process, starting late, driven by a few large galaxies, we have a scenario where many small, efficient galaxies appeared early, together creating enough photons to illuminate the universe. This doesn't contradict reionization. Completing at Z is approximately equal to 6. It just changes the shape of the evolution curve, pushing the starting point earlier and making the process more rushed. And this is where the story begins to intersect with another problem: primordial black holes. If galaxies formed early and strong, if gas collapsed quickly and efficiently, then conditions for black holes to form and grow rapidly also became more favorable. Reionization is not just a consequence of starlight. It may be affected by radiation from active nuclei. At this point, the question is no longer did reionization happen as we think. The question is, what is the relative role of different sources in that process? And are we underestimating the contribution of objects we previously couldn't observe? James Webb doesn't provide the final answer, but it has reset the entire problem, from the assumption level to the data level. And from here, the story must shift to another direction. If light appeared early and densely like this, then what is creating the brightest sources at this epoch? In the traditional picture of the early universe, black holes are not the main character. They're seen as byproducts, appearing after stars had formed, died, and left heavy remnants. According to that logic, black holes need time, a lot of time to grow. James Webb has brought black holes to the center of the story, not because it found monsters, but because it found them at the wrong time. Before JWST, the earliest known supermassive black holes were mainly quasars at redshift around 6.7, when the universe was already 700 and 800 million years old. Even these objects were already a difficult problem, but could still be patched by assuming continuous growth at the Eddington limit. JWST has pushed that boundary back hundreds of millions of years. In data from JADES, Bremer, Sears, and Cosmos Webb, astronomers began noticing a very special population of light sources, small, red, but unusually bright. They don't look like typical starburst galaxies, nor like old galaxies in the modern universe. These sources were later informally named Little Red Dots, LRDs. The name sounds simple, but their scientific significance is not. LRDs typically have effective sizes of just a few hundred parsecs, much smaller than typical galaxies. However, their infrared brightness is higher than what a normal stellar population in such a small galaxy could produce. The first anomaly lies in morphology. In near-cam image, many LRDs look almost like point sources, or have an extremely bright core with very little surrounding structure. This is a sign that light doesn't come from a spread-out stellar disk, but from a very concentrated region. The second anomaly lies in the spectral energy distribution, SED. When research groups modeled LRD SEDs, they found that to explain the observed brightness and colors, they needed a very hot emission component, much hotter than ordinary stars. This is where suspicions about active galactic nuclei, AGN, begin to emerge. James Webb doesn't stop at imaging. It uses NIRSpec to obtain spectra of some sufficiently bright LRDs. And it's the spectra that turn suspicion into evidence. In these spectra, astronomers detect broadened hydrogen emission lines, especially Balmer lines like H-beta. The width of these lines corresponds to gas velocities up to thousands of km's. No ordinary star formation process can create gas moving this fast on large scales and stably. This is the classic signature of gas, orbiting an extremely heavy object, a black hole. Additionally, spectra also show narrow emission lines of ionized oxygen, O3, typically associated with AGN. The combination of broad and narrow lines is the spectral signature of an active nucleus. When analyzing spectra of high-Z galaxies JWST detected, astronomers don't just measure brightness, they look for chemical fingerprints. Each element emits light at specific wavelengths. Oxygen, carbon, nitrogen all leave signatures in the spectrum, and when reading these signatures from Z8 to 10 galaxies, they discovered something unexpected: metals, a lot of metals. In astronomy, metals means everything heavier than helium, and all of them must be created in stars. After the Big Bang, the universe only had H75%, He25%, and a bit of Li. Everything else comes from stars dying in supernovae. The process of chemical enrichment takes time. According to old models, 10 galaxies were supposed to have very low metallicity, around 1 to 10% solar. But NearSpec shows some 8 to 10 galaxies have metallicity 0, E Dao Ling, Uch Solar, an extremely high number for that time. To achieve this, galaxies need multiple cycles: stars born, live, die, enrich, born again. Each cycle takes tens of millions of years. If a Z9 galaxy, 500 million years old, already has 0, 2 solar metallicity, it means it went through at least 2 to 3 stellar generations. This pushes the first stars back to Z15 to 18 or higher. Stranger still, JWST sees nitrogen in some objects. Nitrogen is special because it's mainly created in massive stars, or binaries, through the CNO cycle, a slower process than oxygen. Carbon. Some Z8 galaxies have unusually high N-O ratios, suggesting very massive stars or a stellar population that evolved for a long time. Both require long time scales, contradicting the universe's age. Then, chemical clocks ratios between elements like O, Fe, N-O can indicate the timescale of star formation history. JWST data shows some galaxies underwent chemical evolution much more complex than predicted. This adds more pressure on the timeline. Not only did galaxies form early, but they evolved chemically faster than models allow. One of the most carefully analyzed cases is Kuiper's LRDZ-9. Observed in the Kuiper's program C. Andel's PRISM epoch of reionization survey. NearSpec spectra confirm this object at redshift Z is approximately equal to 9. San. When the universe was only about 500 million years old, from the H-beta line width, research groups estimate the central black hole mass at somewhere from tens of millions to hundreds of millions of solar masses, depending on geometric assumptions and gas disk inclination. This number itself is already a shock. At that time, according to standard models, the entire galaxy was typically only expected to have stellar mass of a few hundred million to a billion solar masses. Having a black hole occupy such a large mass fraction is something that almost doesn't exist in the modern universe. In today's galaxies, central black holes typically only occupy about 0.1% of stellar mass. In some LRDs, this ratio can reach several percent or more. This leads to an uncomfortable conclusion. Black holes grew very fast, faster than their host galaxies. To understand why this is a problem, we need to return to a very basic physical limit, the Eddington limit. The Eddington limit defines the maximum rate at which a black hole can accrete matter in a stable state. When matter falls into a black hole, it emits radiation. This radiation creates outward pressure, pushing matter away. At the Eddington level, these two forces balance. At that rate, black hole mass can double after about 30-50 million years. Now let's place the numbers side by side. Suppose a black hole starts from a light seed, the product of a population 3 star, with mass around 100 solar masses. In 500 million years, even with continuous growth at the Eddington limit, it can only reach a mass of about 10 to the power of 6 solar masses. But JWST is seeing black holes 1 to 2 orders of magnitude heavier than that. At the same time, this means at least one assumption in the chain above is wrong. There are 3 main possibilities. First possibility, black holes grew beyond Eddington for long periods. Theoretically, super Eddington growth can occur for short periods, if the accretion flow geometry allows radiation to escape in other directions. But sustaining this for hundreds of millions of years is very difficult, because radiation feedback will heat and blow away gas. Second possibility, black holes started from heavy seeds. In this scenario, black holes didn't form from stars, but from direct collapse of a giant gas cloud, creating an initial black hole with mass 10 to the power of 4, 10 to the power of 6 solar masses. Third possibility, a combination of both, with rapid growth phases supported by special primordial environments. James Webb doesn't directly see seed formation processes, but it provides observational evidence more consistent with the heavy seed scenario. The reason is, if black holes were already very large from the start, then them occupying a large mass fraction in a small galaxy becomes more understandable. Conversely, if they started very small, catching up to the galaxy in such a short time is extremely difficult. Additional evidence comes from the dust and gas environment around LRDs. Said analysis shows many objects have signs of hot dust, heated to several hundred Kelvin. Such hot dust is very difficult to sustain with stars alone, especially in a small galaxy. But it's a natural consequence of radiation from an actively operating AGN. Parallel observations from ALMA also show some LRDs contain significant amounts of gas, concentrated at the center. This is consistent with a scenario where gas is efficiently channeled into the core, feeding the black hole. More importantly, LRDs don't appear sporadically. They appear as a population in many different JWST fields. This shows that the process creating large early black holes is not a rare exception, but maybe a common formation channel in the early universe. If many small galaxies existed early and formed stars efficiently, then there are also many environments rich in gas, low in metals, and highly turbulent, exactly the favorable conditions for direct gas collapse. In other words, early reionization and early black holes may be 2 sides of the same picture. Additionally, primordial black holes may have contributed to reionization through high-energy radiation, especially X-rays. X-rays have longer penetration than ultraviolet photons, can ionize hydrogen on larger scales, and heat the intergalactic medium. James Webb doesn't directly measure this contribution, but detecting AGN at high redshift forces reionization models to reconsider the role of black holes rather than just focusing on stars. At this point, one thing is clear: black holes didn't wait for galaxies to mature before appearing. In many cases, they may have formed simultaneously, or even before most stars. This reverses the familiar causal order in modern astronomy. And once this order is reversed, all models about galaxy evolution in the early universe must be rewritten in more detail. James Webb doesn't prove that new physics is necessary, but it shows that familiar physics, when placed in extreme conditions, can produce results more extreme than we ever imagined. The final remaining question is not, do black holes exist early? The answer is yes. The question is, how common are they? And how have they shaped the surrounding environment? Looking back at everything James Webb has provided, from record galaxies at redshift above 14 to unexpectedly high galaxy density in wide surveys, to the early appearance of large black holes, the most important thing is not amazement, but correctly identifying where the real contradiction lies. In science, not all tensions have the same significance. Some only require parameter adjustment. Some force changing underlying assumptions. And others, rarer, might collapse the entire theoretical framework. James Webb doesn't place us in that final scenario, but it has placed us in an irreversible position. Some core assumptions about the early universe no longer fit observational data. The first assumption under the most pressure is the pace of structure formation. In the lambda CDM model, structure formation is hierarchical. Small halos form first, then gradually merge into larger structures. This is still true. James Webb hasn't observed anything contradicting the existence of dark matter halos or their dominance over large structure. But what Webb is showing is this process may proceed significantly faster under the initial conditions of the universe. Pre-JWST models were typically calibrated with data from relatively late universe, where feedback from stars, supernovae, and AGN had significantly slowed gas accumulation. When those models are extrapolated backward to Z is greater than 10, they implicitly assume these inhibiting mechanisms also operate with similar efficiency. JWST data is indicating that assumption is too conservative. In the early universe, gas had extremely low metallicity. This changes how it cools, how it fragments, and how it responds to feedback. Cold gas streams can feed halos continuously, rather than being easily blown away. The result, halos can reach the threshold for efficient star formation earlier. This doesn't require changing the nature of dark matter. It only requires us to acknowledge that the boundary conditions of the early universe fundamentally differ from the modern universe. And directly applying effective formulas from Z0 to Z15 is no longer reasonable. The second assumption being challenged is star formation efficiency. But high efficiency is only half the story. The other half lies in the question, why didn't anything stop it? In the standard model of galaxy formation, when stars form, they don't just create light. They create feedback, a form of energy returning to the surrounding environment and slowing, even completely stopping subsequent star formation. There are three main types of feedback. First is stellar feedback, feedback from stars. Massive stars emit strong stellar winds, and when they die in supernova explosions, enormous energy is released. This energy pushes gas out of the galaxy, or at least heats it to the point where it can't cool back down and collapse to form new stars. Second is AGN feedback, feedback from the central black hole. When a black hole accretes matter, it ejects energy in the form of radiation and plasma winds. These energy streams can blow gas away from the galaxy center, cutting off fuel supply for both the black hole and stars. Third is radiative feedback, radiation feedback. Ultraviolet light from young stars ionizes surrounding gas, increasing pressure and preventing gas from further collapse. This is an important mechanism in regulating star formation in small galaxies. In the modern universe, feedback is extremely effective. This is why dwarf galaxies today form stars very slowly. Supernova explosions continuously blow away gas before it can cool back down and create the next stellar generation. Lambda CDM models assume feedback operates similarly, or even stronger, in the early universe, because galaxies then were smaller, lighter in mass, so gravity was weaker, and theoretically, gas was easier to blow away. But James Webb is showing the opposite. Many small galaxies at Z8 to 10 have very high star formation rates. extremely blue spectra, and very little dust. Feedback doesn't seem to restrain them. Something in the early universe environment made feedback less effective than predicted. There are three main reasons. First reason is low metallicity environment. In the modern universe, when a star explodes in a supernova, energy is efficiently converted into gas kinetic energy through radiative cooling processes. Metals, especially oxygen, carbon, silicon play an important role in cooling gas, helping it radiate energy away quickly. The result is the gas shell blown outward can reach very high velocities. But in the early universe, where metallicity is extremely low, this cooling process is much less efficient. Energy from supernovae doesn't convert into kinetic energy efficiently. The result is gas isn't blown away as strongly as predicted. Part of the energy is wasted as heat, rather than becoming motion. This means stellar feedback in the early universe was weaker than in the modern universe, even when supernova numbers are the same. Second reason is cold gas streams. In computer simulations of the early universe, cosmologists discovered that gas doesn't just fall into galaxies uniformly. Instead, it can fall in along cold streams, dense, narrow gas flows, not heated by shocks when penetrating through dark matter halos. These cold streams penetrate straight into the galaxy center, continuously supplying new fuel for star formation. Even when feedback blows hot gas outward, cold streams continue pouring in from other directions. The result is gas inflow rate can be larger than the rate at which feedback can clear gas. In that case, stars continue forming despite feedback. Third reason is compact morphology. Many galaxies JWST detected at high redshift have extremely compact sizes, just a few hundred parsecs, about 1,000th the diameter of the Milky Way. In such small space, gas is concentrated very densely, and gravity is relatively strong compared to size. Feedback needs to overcome gravity to blow gas outward. In a compact galaxy, this energy threshold is higher. In other words, feedback needs to be much stronger to escape from the galaxy's gravitational well. This explains why many small galaxies in the early universe can maintain high star formation rates without being choked by feedback. When combining all three factors, weaker feedback due to low metallicity, cold gas streams continuously supplying fuel, and compact morphology making gas hard to escape, the picture becomes clear. The early universe was not a place where feedback regulated star formation as efficiently as today. Instead, it was an environment where gas could fall in quickly, cool quickly, and form stars quickly, before feedback could intervene. This is not new physics. This is just familiar physics, operating in a different regime, before Webb, to avoid creating too many stars early. Models typically assumed low star formation efficiency in small halos. This was consistent with today's dwarf galaxies, where strong feedback can choke star formation. But James Webb is showing that many small early galaxies are not weak. They emit large amounts of ultraviolet light, have very blue spectra, and show very little dust. This is consistent with young, massive stellar populations and high gas-to-star conversion efficiency. More importantly, the number of these galaxies is large enough to have statistical impact on the entire universe, not just exceptions. This forces models to reconsider the assumption that small galaxy equals inefficient. In the early universe, the opposite may be true: small, compact, dust-poor galaxies are the main engines of early evolution. The third assumption, and perhaps most irritating, is the formation order between galaxies and black holes. In the modern universe, the correlation between central black hole mass and galaxy stellar mass m sigma relation makes us accustomed to the idea that black holes follow galaxies. Stars form first. Then black holes grow gradually through accretion and mergers. James Webb is showing that in the early universe, this order isn't always true. The existence of LRDs, with black holes occupying large mass fractions, at times when the universe was only a few 100 million years old, shows that in some systems, black holes developed very fast, even faster than most surrounding stars. This doesn't break physics, but it breaks a convenient assumption that black holes are always latecomers. When this assumption is removed, many consequences emerge. Primordial black holes may have strongly influenced gas flows, regulating or even promoting star formation. They may contribute to reionization through high-energy radiation, and they may shape early galaxy structure in ways current models haven't fully described. However, and this is an extremely important point, no pillar of modern cosmology has collapsed. James Webb doesn't show any signs that the universe's age is wrong. There's no evidence that the Hubble constant is broken in a radical way. No observations force abandoning dark matter or dark energy. Cosmic microwave background radiation still fits lambda CDM. Large structure distribution still matches predictions at scales of hundreds of millions of light years. What Webb is doing is peeling back the detail layer at small scales and early times, where data was previously too poor to verify. In other words, the model's skeleton still stands firm, but the soft tissue needs restructuring. This reflects a familiar rule in scientific history. When new data opens a new observational domain, assumptions built to fill gaps are typically the first to be replaced. Not because they're wrong, but because they were born under data-scarce conditions. James Webb is erasing that scarcity. Another important consequence is how we should interpret the phrase young universe. For many years, young was implicitly understood as undeveloped. But JWST data is showing that young doesn't mean slow. The universe may have entered a violent growth phase very early, where familiar physical processes, gravity, gas cooling, star formation operated at much higher intensity than later periods. If true, then the fact that today's universe looks more gentle may not be the default state, but the result of billions of years of accumulated feedback that slowed everything down. James Webb allows us for the first time to directly observe the epoch before that slowdown occurred. And this is the key point to lock down the big topic. What James Webb is revealing is not a strange, illogical universe. It is a universe more consistent with physical laws, when those laws are placed in their own most extreme environments. The universe didn't cheat to create early galaxies and black holes. It just operated physics in a regime we previously never had the ability to observe. Looking at it that way, current paradoxes are no longer signs of collapse, but maps pointing to areas where our understanding is still crude. And most importantly, James Webb hasn't finished the story. It has only opened the first chapter of an observational phase that previously only existed in simulations. The final question is not, is the universe wrong? The question is, how much have we underestimated the early universe? Just because we never saw it clearly, like now, that's where the story can stop, not with a definitive conclusion, but with a new boundary of understanding, just pushed back. For a very long time, the early universe existed for us, mainly as a gap in models. We knew it had to be there, knew it was important, but couldn't look straight at it. Therefore, we had to fill that gap with assumptions that everything started small, slow, and simple, then gradually became complex. James Webb has put an end to that phase, not with a single discovery, not with a record galaxy, but by transforming the blind spot of cosmology into a data-filled region. When that region was illuminated, what emerged was not a chaotic or illogical universe, but a universe operating very seriously, just faster. more violent, and more efficient than what we had assumed. Galaxies didn't wait for enough time to form. Stars didn't queue up at the familiar pace of the modern universe. Black holes didn't necessarily have to be latecomers. Under those initial conditions, when gas was still pristine, when feedback hadn't yet accumulated, gravitational physics and radiation pushed the evolution process to a completely different rhythm. The important thing is, no laws were broken. No need for exotic physics. No need to rewrite the Big Bang. No need to erase dark matter or dark energy. What needs changing is not the foundation, but how we simplified the processes occurring on that foundation. James Webb doesn't give us a new universe. It gives us a new perspective on the same universe, at exactly the moment we previously never had the ability to observe. And when perspective changes, the story naturally must be retold in more detail, more carefully, and more honestly with the data, possibly, in the next few years. Some initial conclusions will be adjusted. Some objects will be reclassified. Some numbers will be refined. That's not a sign of instability, but how science advances when data continues pouring in. But one thing is almost certain won't change: we've underestimated the maturity level of the early universe. Not from lack of understanding, but from lack of observational capability. Now, that capability exists. And when looking at those faint light dots from over 13 billion years ago, we're not just seeing the first galaxies, we're seeing our own old boundary of understanding, being pushed back once more, not by imagination, but by real light, from a universe once young, but never slow. If you want to follow what James Webb continues to discover in the coming years, when it pushes observational boundaries even deeper, when larger catalogs are published, when missing puzzle pieces are gradually filled in, then don't forget to subscribe to the channel, because the story of the early universe isn't finished. It has only just begun being told truthfully.